In this video, I will provide a quick introduction to the kinematic equations in the field of physics, and I'll show a couple examples of how to use these equations. So let's jump right into it. Here are the four kinematic equations in the field of physics. Now, these four equations describe the motion of objects under constant acceleration. So we can only use these equations to solve problems when we have constant acceleration. So let's walk through each of them. The first kinematic equation says that the final velocity, so v sub f, of some object is equal to the initial velocity, so v sub I, plus the acceleration times time. Now, I should also mention that sometimes you might see this equation written like this. V is equal to v naught plus a times t, where v, this represents the final velocity, and v naught is the initial velocity. So occasionally you might see it written like this instead. For this video, we're just going to use this syntax though. Okay, now the second kinematic equation says that the displacement of some object is equal to the initial velocity times the time plus 1/2 times the acceleration times time squared. Then the third equation says that the final velocity of some object squared is equal to the initial velocity squared plus 2 times the acceleration a times the displacement of the object. And lastly, the fourth equation says that the displacement of some object is equal to 1/2 times the initial velocity plus the final velocity times time. And again, I've made a note down here that says acceleration must be constant and it must be non-zero in order for us to use these equations. So let's take a look at two different examples of how to use these kinematic equations to solve some problems. So let's take a look at this first example. An airplane accelerates down a runway at 3.20 meters per second squared for 32.8 seconds until it finally lifts off. Determine the distance traveled before takeoff. So when we're solving these types of problems, the first thing we want to do is write what are we given. So what variables are we given? So let's write that first. Well, we're told that the plane accelerates down the runway at 3.20 meters per second square. So this is the acceleration, the constant acceleration. So we're given A. We're also given the time, 32.8 seconds. So we're given T. And although it doesn't explicitly say it, the airplane, we can assume that it starts from rest and then it accelerates. So we're actually given the initial velocity, which is v sub I, the initial velocity, and that's going to just be 0 meters per second. And what we're trying to find, let's write that, we're trying to find the distance traveled before takeoff. Now, in this scenario, we have some plane, let's say it starts right here, and then it travels for 32.8 seconds to some point out here. So this distance right here, this is actually going to be the displacement. Because remember, the displacement of some object is just the final position minus the initial position. So really what we're trying to find is the displacement of the plane. So let's write that, displacement. So now once we've written out all of these variables that were given and the one that we want to find, we can then look at these kinematic equations and say, okay, which one of these will allow us to solve this problem? So what we're going to do is we're going to look for which equations contain these four variables. So if we take a look at the first equation, we can see that this equation involves the final velocity, which we are not given. So we are not going to be able to use this equation. This second equation, this involves displacement, initial velocity, time, acceleration, and time again. So we have all of these variables, so we can actually use this equation to solve this problem. And if we were to look at this third equation, we would notice it also involves the final velocity of the object, which we don't have, so we can't use that equation. And similarly, the fourth equation also involves the final velocity of the object, so we also can't use that one. So to solve this problem, we're going to use this second equation right here. So let's go ahead and write that down. We'll say the displacement of the plane is equal to, we have the initial velocity times the time. So again, the initial velocity is going to be 0 in this case. The plane starts from rest. The time is 32.8 seconds. And then we have plus, we're going to add 1/2 times the acceleration. So we're given the acceleration, that's 3.20. And then we multiply that by the time squared. So again, the time is 32.8 seconds squared. So if we simplify a little bit, this part of the equation is 0, and then we have plus this part of the equation. If you punch that into a calculator, that comes out to 1,721.34. So our final displacement is simply going to be 1,721.34, and that will be in terms of meters. so that is the displacement of the plane. So that's our answer for that one. Now let's check out the second example we have here. A bike accelerates uniformly from rest to a speed of 7.10 meters per second over a distance of 35.4 meters. Determine the acceleration of the bike. So again, to solve this problem, let's write down what are we given? What variables are we given? Well, we're told that it starts from rest. So our initial velocity, again, in this case is going to be 0. So we're given the initial velocity. We're also given the final speed is 7.10 meters per second. So this is going to be our final velocity. So we're also given v sub f. And then we're also given a distance of 35.4 meters. So again, in this example, we have some bike. Let's say it starts here, and then it travels this way for 35.4 meters. So this distance right here, again, this is going to be the displacement of the bike. So we'll say we're also given the displacement, and we want to find the acceleration. So we'll say find A. So again, we're going to take a look at these four variables that were given, and we're going to look at our four kinematic equations and see which ones contain these variables. So for this problem, one thing we'll notice is that we are not given the time. And what we'll notice in our kinematic equations over here is that the first equation, the second equation, and the fourth equation, all of these involve time, t. So we're not going to be able to use any of those equations to solve this problem. So by default, we'll have to use this third equation, which involves final velocity, initial velocity, acceleration, and displacement. And these are the four variables that we're working with in this example. So we're going to go ahead and use this third equation. So first let's write the final velocity squared. So again, the final velocity in this case is 7.10. So we'll write 7.10 squared. That's equal to the initial velocity squared. So again, the bike starts from rest. So the initial velocity is 0. So we're going to have 0 squared, and then we add 2 times the acceleration a. So we don't know a, we're trying to figure that out. And then we multiply that by the displacement. And the displacement is 35.4. So we'll say 35.4. So if we simplify a little bit, 7.10 squared, that turns out to be 50.41. Is equal to, on the right hand side we have 0 squared, which is just 0. Then we have 2 times 35.4, that turns out to be 70.8, and that's multiplied by a. So we'll say a. So to solve for a, we can divide both sides by 70.8. So on this right hand side, these will cancel out, and we'll be left with a is equal to this quantity. This turns out to be about 0.712, and we're talking about acceleration, so our units will be meters per second squared. So that will be our answer for this one. The acceleration is 0.712 meters per second squared. So those were just a couple quick examples of how to use kinematic equations to solve problems involving motion. And just keep in mind that when you're trying to solve these problems, always write down what variables you're given and what variables you want to find. And then you can just look through these four kinematic equations and determine which equation contains all of those variables.